I'm Keshav Vasantabada, Marketing Specialist for Protein Services at GenScript, and I'm here to kick off our webinar today by introducing the presenter, Hongxing Yu. Hongxing is a senior scientist in the GenScript protein production group. She got her PhD in biology from Friedrich Schiller University in Jena, Germany, with specialization in medical biology. Hongxing has extensive experience in protein interactions between hosts and pathogens using different expression systems. The topic for today's webinar is analyzing antibody sequence for recombinant antibody expression. In this webinar, Hongxing will review some antibody basics and see how sequence information correlates with its heterologous expression in mammalian cells. She'll also provide suggestions on how to efficiently evaluate antibody sequence in order to come up with the ideal cloning strategy prior to expression testing. To ensure the sound quality of this webinar, all attendees have been muted. To ask questions, just type your questions in the chat box so Hongxing can address them towards the end of the session. I also want to let you know in advance that a quick poll will show up at the end of the webinar. It would be great if you could take a moment to provide feedback about today's session. And with that, without any further ado, I'll hand over to a presenter. Welcome, Hongxing.
Okay, thank you, Keshav, for your introduction. Good morning, ladies and gentlemen. Welcome to my session in our webinar series. So like Keshav introduced to you, my presentation today will focus on analyzing the antibody sequence for recombinant antibody expression. This presentation today will be broadly divided into 4 topics. Firstly, I will talk about the antibody basics, structure, and function, then go forward to how the antibody is produced. And then I would like to introduce you some online antibody database and also some sequencing analyze tools. And then I would like to give you some case studies which we use to optimize the antibody production. So in the end, I will answer the submitted questions you typed in. Okay. So firstly, let's have a look at the antibody basics, structure, and function. So probably you already know that the antibody, also called the immunoglobulin, is a very large very protein produced by the plasma cells, also called activated B cells. So here is the shape of the wave protein, the antibody, and it consists of 4 polypeptide chains, the 2 heavy chains here, and the 2 light chains here. And those chains were connected by the disulfide bonds. The immune function of the antibody is to identify and neutralize the pathogens like the bacteria or viruses, because the antibody has the ability to recognize the unique molecule from these antigens, so by here. Okay. So the antibody can come in different varieties known as the isotypes or classes. In mammals, there are 5 antibody isotypes known as AGA, AGD, AGE, AGM, and AGG. So they are grouped based on the heavy chain they possess, the alpha, delta, epsilon, mu, and the gamma chain. These isotypes also differ in their biologic properties, functional locations, and their ability to deal with different antigens. For example, the AGA is major located and plays roles in the mucosal area. And AGD functions mainly as the antigen receptors on the B cells, which has not been exposed to the antigen. And AGE is more responsible for the allergic response, and AGM could eliminate the pathogens in the early stage of the B cell mediated immunity. The AGG is most popular, which provides the majority of the antibody-based immunity against the invading pathogens. So the basic unit of antibody is the immunoglobulin monomer, like the AG, D, G, and E. The secreted antibody, for example, the AGA, it could be also dimeric with 2 AG units here, and also pentameric with 5 AG units could form the AGM. So as I showed before, that the AG monomer is a V-shaped molecule. The arm of the V contains the sites which can bind with the antigen, and this can recognize the bacteria or virus, the invading pathogens. And the N terminal of the region called so this arm called Fab region is fragment of antibody binding region, and the N terminal of the antibody is the viral domain. This is called FV region, and this is more specific for more important for the binding to the antigens. And in the FV domain, there are 6 loops of the beta strands, which are plays more critical roles on the antigen binding, and these loops are referred to as the complementarity determining regions, also called CDRs. And the base of the Y play important role on modulating the immune cell activity. And this region called FC region, and it's composed of 2 heavy chains. Yeah, the light chain is there, and it's composed to the heavy chain. So the FC region ensures each antibody could generate the immune response for one given antigen by binding to the FC receptor or other immune molecules like the complement proteins. So to summarize that the Fab region could determine the antigen specificity, and the FC region determines the effect of the immune effect of the antibody. And there are also a hinge region which is quite flexible and could connect the Fab to the FC part. So how does the antibody bind to the antigen? So as we know, there are several types of antibodies and antigens, but each antibody only able to binding one specific antigen. And the antibody-antigen binding interactions are based on the non-covalent binding. And the hinge region I just mentioned, which can connect the Fab to the FC, which can open and close to allow the better binding of the antibody-antigen. So from this picture, you will see that the antibody-antigen interaction mainly by the spatial complementarity, which shows like a log and K interaction. And the antigen could bind to the antibody through very weak and non-covalent bonds, for example, the electrocentric interactions, the hydrogen bonds, the van der Waals forces, and hydrophobic interactions. So in other words, this means this binding is weak and is reversible. The CDRs is the most important part for binding to the antigen. Here is the structure of the CDRs. Here we could show this loop. There are 6 loops, as I mentioned before. It's composed to the antigen binding site. 3 from the light chain and 3 from the heavy chain. In this loop, the CDR H3, which is more variable in the sequence and length, and the CDR L3, which mostly occupy the center of the binding site. So both of them tend to make the K contact with the antigen. So now we know that the basics of antibodies. The next question would be, how is an antibody produced in vivo? Antibody could actually occur in 2 physical forms. One called the memory binding form, and this is a part of the B cell receptor. And another form is a soluble form, which is secreted from the activated B cells, and more specifically, it's from the differentiated plasma cells. So when the B cell receptor recognize and attach to the antigen, these antigens could be further internalized and processed. Within these B cells, the fragment of antigen could be combined with the HLA class 2, and the HLA class 2 antigen fragment complex could be displayed on the B cell surface. So here. So this is what we call the first signal. And then the T helper cells could also recognize the complex of the HLA class 2 and antigen fragment complex. And then these T cells could be activated to produce cytokines. The cytokine can further activate the T cells. This is what we call the second signal. Once the B cells are activated, they could differentiate into the plasma cells. Those cells can secrete the soluble antibodies. So now the question is, how does the B cell produce the unique antibody specifically binding to the certain antigen? Actually, to achieve this, the body generates a very complicated mechanism called VDJ recombination, also known as the antibody gene rearrangement. The variable chain, the variable region of each heavy or light chain is encoded by, you could see from this picture, by several pieces known as the gene segments. So there are several gene segments, and these segments are called variable, V, diversity, D, and the joining segment, the J. So in the bone marrow, each developing B cell will assemble one variable region by randomly selecting a combination of only one V region, one D region, and one J region. So since there are many copies of these gene segments, so you could imagine that different combination of these segments could generate a huge number of antibodies, each with different paratopes and has different antigen specificity. So once the B cell produces a functional immunoglobulin gene during this VDJ recombination, this kind of B cells cannot express any other variable region. So this means each B cell can produce antibodies containing only one kind of variable chain. However, the activated B cells also have other mechanisms to modify the antibody. So one of the mechanisms called somatic hypermutation, and this by this the gene encoding the variable region, the variable domain, could undergo a high rate of point mutation. So as the consequence, any daughter B cells will possess only slight amino acid difference in the variable domain. So another mechanism is called class switching. So this is used to generate the different classes of the antibody. Also, that's what we mean the isotypes. So all these antibodies with the same variable domain, but possessing distinct contact regions. So this allows the different daughter cells from the same activated B cell to produce antibody binding with the specific antigen, but with different isotypes or subtypes. So how the antibody produced? In today's the Hybridoma technology is very popular to be used for the antibody generation. This technology can allow to form the hybrid cell lines by fusing the antibody producing B cells, which isolated from the immunized mice, and fused with a myeloma cell, which is a kind of cancer cell. And this fusion could allow the antibody production of with one single specificity, and therefore they are called also monoclonal antibodies. So I won't go details for this technology because our antibody department, they have more experience for this. But the production of so it worth to mention that the production of this technology is was invented by Meissner and Kühler. Both of them won the Nobel Prize in 1984 for medicine and physiology. So I would introduce you the process used for recombinant antibody. It's like here I showed in this slide. So first you generate the hybridoma cells, and so the antibody generated from the hybridoma cells could only recognize one specific antigen, and then you got the antibody sequence from the hybridoma cells. After you get the sequence, you do the gene synthesis and subcloning to your expression vector. And using this expression vector, you can do the transient expression for small-scale production of the antibody, and then do the function analysis for their antigen-antibody binding affinity. And then you select the target interested antibody for your further experiments. You can do the scale-up production. So if you have very large-scale usage for the antibody, you can also perform the stable cell line or cell pool development, and this allows you to get the GLP or cGMP levels of large-scale production. So before we start the production of those antibodies, of course, the most important thing is to evaluate the efficiency of your antibody sequence. So there are a lot of online tools which can help you to analyze the antibody sequence, especially on the CDR part. So here I list you some of them, like the BioInk, the IMGT, the ABCheck, IGBlast, and also give some links for the sequence alignment tools. So you could easily use them for evaluating your antibody sequence. So later on, I will give you one example how to really analyze your certain sequence. But before that, I would introduce you a scheme called Cabot numbering scheme. And this is a scheme for numbering the amino acid residues in the antibody viable regions. This scheme was developed from the antibody sequencing data, and if I remember correctly, the current Cabot database contains over 6,000 light chains and almost over 8,000 heavy chains. So you could imagine that it's quite efficient for you to compare your viable regions of your sequence among the huge database. And in this picture, I list here, you will see that the numbering throughout the viable regions of the heavy chain and the light chain. So there's one thing I would like to especially mention to you is here in the CDR heavy chain, the insertions between the residue H100 and H101. So in the database, we found that there is a potentially long insertion between these two residues. So in such situation, these insertions will be numbered with letters, for example, the H100A, H100B to K, and then go to the H101. So the other website, the IMGT website, could offer you a structure analysis for the antibody. For example, this picture is a typical 3D structure of one Ag monomer. So you could easily see the different domains of each heavy chain. So you will see the heavy chain and the light chain with different colors. And you can see that from each variable chain is composed by a lot of beta strands. In this picture, it's more clear. And you will see that there are 9 strands with 3 loops. And these 3 loops is what I mentioned before. I refer to be the CDRs. And this is a model which could also show you the overview of the relation between the amino acid residues and the beta strands. And here, the loop here is also the CDRs. So now from the database analysis, the people find that there are certain rules which can specify the CDRs only from the antibody sequence by looking at the antibody sequence. For example, this one here for the CDR L1, it always starts with 16, and end with tryptophan. So I won't go details on the certain rules of each CDR. Here is the same with the heavy chain. These rules are very popular used for the CDR identification. Of course, it can't be 100% feasible, but it works very well because it is based on the very huge antibody sequencing database. So to show you how to identify the CDRs by a certain sequence, here I summarize these rules and for your better understanding. And here I give you a sequence which we can do our own CDR identification. For example, here we find in the CDR-L1, it always starts with the C, the cysteine, and end with the tryptophan. So in this domain, we will define it as the CDR-L1. And the CDR-L2 is start with the IY, and the length is always the 7 residues. And the CDR-L3 is between the 15 and the FGXG. So it's quite easy to find your specific CDRs by only using these rules. And the same also for the similarly also for the heavy chain. So based on our experience, you could easily define these CDRs by these rules, like I said before. So it can't be 100% correct, but sometimes you can easily use these rules. If you want to if you want to analyze the whole viable chain, then you can use the the antibody check website. This is even more easier. You can just select your viable region of both heavy chain and light chain, and submit them in this website. Then the sequence will be automatically blasted based on the database. So, like I showed here, any unusual residues, if it occurs only in less than 1% of the chains in the database, will be reported to you, and this allows the identification of the potential sequencing errors. For a good sequence, like I showed you here, so it only has 2 unusual sites. So you will see that the L7 and L106. But sometimes, if you have not a very good antibody sequence, you may observe more unusual residues and sometimes even longer insertions. So what we could do for you, the GenScript will help you to get the optimized antibody production. So we could supply you the whole service line for antibody production from the gene for the hybridoma generation, gene sequencing, and then go from the gene synthesis, small-scale evaluation, and also go to the stable cell line or cell pool-based large-scale up production. And besides, we also supply you the sequence designation service, for example, the sequence analyze, and sometimes we can also do the small unusual residues revision for you. And we have our special codon optimization system for according cell line, and this can allow the efficient transfection and purification, so to achieve the high antibody production yield. What are our advantages? So we have the prominent suspension systems to promote large-scale and fast delivery of the recombinant antibody up to gram level. And we also have many years of experience in antibody production, and we have highly productive stable cell line generation. And we can also offer you professional process development to enhance the antibody expression and production. So in the past time, we have successfully delivered over 800 antibodies with over 100 stable cell lines. So in-house, we have licensed several expression cell lines from the NRC. For example, the HEX293 and the CHO cell line. And both cell lines could adapt to the serum-free system, which allows the rapid and high-yield recombination protein production. And these cell lines are also has the viability for the cGMP production, so you can easily use for your downstream industry usage. So recently, we also we have launched manpower guaranteed recombinant antibody production service to meet the increasing demands of the high quality antibody production. So in this package, antibody amount, the purity, and also the endotoxin level will be guaranteed for you. And you just easily provide the antibody sequence. We will do the evaluation of your sequence, and then you just leave it to us, and we will deliver the antibody at the amount and the purity you specified to us. And it was also worth to be mentioned that we have very fast turnaround time, and we can deliver you the antibody within 5 weeks. So here I also would like to share with you one case study we did before. From this study, I would like to show you that how efficient we could improve the expression level. This order is for 15 milligram guaranteed antibody production. However, when we do the evaluation of the small evaluation, we found that the expression level of this antibody was extremely low. It only achieved 2.5 milligram per liter for expression level. So you could imagine to obtain 50 milligram antibody, we may need at least 25 liters of the transfected cell culture, which is really very huge. So to increase the expression level, we have redesigned the antibody sequence, and we made the column optimization. We use our designed signal peptides, and then we use we also optimize the transfection and the purification process. So in the end, we deliver 50 milligram antibody only using 2-liter expression system, which means we have achieved the 25 milligram per liter expression level compared to the original 2.5 milligram per liter. Okay, I hope this is convincing evidence for you to believe the efficiency of our production. So to summarize my presentation today, we know that the antibody is large Y6 protein could be used by the immune system to neutralize the foreign antigens. And we also know that the antibody antigen binding residues are mainly located in the CDRs. The important thing is the evaluation of your antibody sequence could assist you to estimate the expression level of certain antibody. So most importantly, I would say here is our company GenScript could offer you the professional service for the optimized recombinant antibody production. Now I would like to hand this over to Keshav, and then I will have a little bit time to look at the questions you typed in. So, Keshav?
Thank you very much, Hangxing. I really enjoyed your presentation. Could you advance to the next slide, please?
Yeah.
Thank you. So I see that we have questions coming in, but before we go there, I just wanted to take a few minutes to tell our audience a little bit about GenScript. So headquartered in Piscataway, New Jersey, GenScript is the world's leading biology research service company with gene synthesis, peptide, protein, antibody, cell line, and discovery biology service capabilities. We are internationally recognized as a leading contract research organization specializing in biological research and early phase drug discovery services. So we provide services and products to scientists in 86 countries around the world. We have built the best-in-class capacity and capability for biological research services, encompassing gene synthesis and molecular biology, peptide synthesis, custom antibodies, protein and antibody expression, and protein engineering, and in vitro and in vivo pharmacology, and all this with the goal to make research easy. I'd also like to let you know that there are more than 10,000 peer-reviewed journal articles that cite GenScript services and products, making GenScript the most frequently cited contract research organization in the world. I hope you'll take some time to visit our website and check out the many ways in which we can help accelerate your research. So with that, let's go back to Hongxing, who will be addressing the questions that are coming in. Back to you.
Thank you, Kashaf. So now you see I got the question, which is the best cell line to use for recombinant antibody production. That's a good question because we have the CHO cell line, the CHO, and the 293 cell line. And one is from the mice source and one is the human source. So if your antibody sequence is originally from the Hybridoma sequencing, so it's assumed to be the mice source, you can use the CHO cell. And if you would like to make the mouse and the human chimeric antibody, then you can try both cell lines because we don't know which would be the optimal one. So normally we would suggest to do a small evaluation in both cell lines, then choose the better expression level for your scale up. I got another question. It's called, what about the modified antibody? For example, a fusion of antibody with another protein. So normally we do the fusion of antibody with another protein is we can combine the, use the protein fused with the Fc part of the antibody, because the Fc part of the antibody could help the protein for the better expression level. It also helps for the purification. We have some good case studies for that also. I hope I explained this in a clear way. So how could we? So another question is, how could we determine the secretion signal sequence? So this question you don't need to worry about because we already developed a large a large library for different signal peptides, and we will test this peptide and choose the best for you. So now for our guarantee package, we already use this signal peptide, and as I showed you in my presentation, in the case study, we also changed the signal peptide, which also helps for the better secretion and for better expression level. So I also see a question that said your manpower recombinant antibody package only provides up to 500 milligram of antibody. What if I need more? Yes, that's a good question. If you have a big usage of your antibody, then you probably could go to the stable cell line or cell pool based scale up, because this could will offer you a more efficient and more powerful system for long-term usage of long-term production of antibody. At the moment, we have our GS system-based stable cell line and cell pool, and I believe our we have already launching this package in our website. If you are interested, you can just look at visit our website, and you will get more information for that. So I got another question. How can I get a quote for your recombinant antibody production service? So you could get a quote by visiting our website, clicking on the quote button, and submitting the necessary information. So you could also email or call us directly using the contact information listed in our website. So assuming that we have all the necessary information from you, our technical account manager will get it back to you within 24 hours for your code. So Keshav, I think that's all questions I got. If I didn't miss anything, did I?
Okay, is that all, Hangqing? All right, so thank you very much, Hangqing, for answering all the questions. So before we end the session, just wanted to inform our audience about the final webinar in our series coming up on June 3rd. If you could just advance to the next slide. Okay, thank you. So yeah, the final webinar in our series coming up on June 3rd. The topic is expression vectors, how to choose or customize vectors for gene and protein expression. And it's presented by Rachel Spear, technical writer, GenScript. I also wanted to remind you that the slides and recording of today's webinar will be archived on our website, along with the slides and recording from all our previous sessions. So I encourage you to visit the website link shown on this slide here and take advantage of these information-packed resources. And if you have any questions that come up later, feel free to contact Hangqing using the email shown here on the slide. So with that, we end today's session. And as I said at the beginning, it would be great if you could take a moment to complete a quick poll right after the session ends to tell us how you like this presentation. Your feedback will also help us to improve our services. So again, thank you all for your time and kind attention. And on behalf of the entire GenScript team, we wish you all success in your research. Thank you very much.